In 2019, three message authentication code algorithms are specified as IEC standards for message authentication codes. These are called LightMake, Sudex Key Mode, and CSEC 12. So let's focus on LightMake and CSEC briefly. So LightMake, designed by Lux, Prenel, Tischhauser, and Yasuda in 2016. This algorithm is somewhat similar to PMAC. The picture might be similar to it. We haven't seen PMAC, but I'm mentioning it because PMAC is covered by some patents, but LightMake is not, because here the counters used here are based on Bernstein's protector counter sum. So LightMake is assumed to be not covered by patents. So idea is as follows. This MAC operation is based on a block cipher. You're again choosing a block cipher, but you're also choosing two keys, K1 and K2. Idea is as follows. You have your message here, but instead of putting your message blocks into the block cipher as an input block, you put a counter in front of it. So this 1s, 2s actually counters. So this is your first counter, this is second counter. But how many bits it uses depends on the s value here. So you choose it. So you can choose it almost half of the message block. So you have the counter, message block, counter, message block. So you are encrypting it and XORing it. So it's a very light operation. This is why it's called LightMake. But here we have a disadvantage here because we are actually spending half of the message block to a counter. So for instance, let's assume that we are using AES here. So our block size is 128 bits. So if you have two blocks, which is 256 bits, since we are using counters, now it's becomes four encryptions here. So it is twice the number of encryptions you need to perform. And at the end, you perform a padding here, 1 and as many as zeros that are necessary. And finally, you perform a final encryption, but this time you are using a different key. And then if there is a truncation needed, you perform it and produce the tag. So it is a very simple design. This is ISO's standards for lightweight MACs actually. So these standards are for lightweight message authentication codes announced in 2019 by ISO. So let's move on to CSEC. This is an algorithm which is efficient for 32-bit microcontrollers, designed by Muha, Menik, Herwege, Watanabe, Prenel, and Verbaughede in 2014. So there are two pictures here because the algorithm depends if the message is multiple of the block size. So it depends if you need a padding or not. So in the first picture, you need a padding. So when you need the padding, you use the first picture here. So idea is as follows: you divide your message into blocks here, M1, M2s, and assume that we have L many blocks. But this block is the last block is not the is shorter than the block size, so you perform a padding here. Idea is as follows: you XOR your first message block with your secret key, perform a permutation pi, which I will show the picture in the next slide. Then XOR it with the second message block, perform permutation, and so on and so forth. And at the end, you perform another key XOR, this time K2, but K2 is actually derived from K by simple shift operations, actually. Then you perform a final permutation, again XOR with the key, and if you need to perform a truncation, do it and produce the tag. So the picture is very simple. But if you don't need a padding, this time in this picture we are removing this padding, and instead of K2s, we are using K1. This is a precaution to avoid actually forgeries. So this is why they consider two cases where there is padding and there isn't. So this picture is really simple, but the security actually depends on the permutation pi. So as you might remember from the previous slide, we said that this was algorithm called CSEC 12. So this pi permutation applied 12 times all the time. So pi is actually this permutation, which is repeated 12 times. So it is very simple. Your input is actually divided into 4 parts. And all the operations here are XORs, modular additions, rotations to the left. And that's all. And here you have a swap operation. So it's a very simple permutation. But for this reason, it is really fast. And you can, here it is chosen as 12 because it is assumed that it is, with this choice, it is fast and secure. So in standards, it is 12. So I took this picture from the official paper. Actually, here they're actually comparing their algorithm, CSEC, with the AES in ECB and CMAC modes on different microcontrollers, which are 32-bit microcontrollers. So they show that in terms of speed, CSEC is really good and requires little amount of memory, let's say.